We said that when a wave encounters a boundary, one of two things can happen. What are those two things? What's one? Tyler? No? Reflection. So reflection can take place when a wave encounters a boundary between the medium it's in and some other medium. What's the other thing that can take place besides reflection or bouncing off of the boundary between those two media? Yeah, I'd take that. Okay, that's not the word I was looking for, but I'd take that. Bree said refraction. What's the general term that I'm looking for here? Transmission, yeah. Now, when it's transmitted, if it goes in at an angle, it's going to be bent. The direction's going to change, which means it's refraction. So I'd take either one, but the term that I'm looking for is transmission. Now, you're always going to get a little bit of both phenomenon taking place, some reflection, some transmission. Depends on how close the materials are to each other, how similar they are to each other, how much of each one you're going to get. If they're really, really similar, Joseph, then you're going to get mostly transmission. If they're really, really different, then you're going to get mostly reflection. The part that's reflected, whether it's just a little bit or whether it's most of the wave that's reflected, can be reflected either right side up or upside down. Now, the last couple of days when we reviewed this, we've gone through and said, okay, when's it going to be reflected right side up? When's it going to be reflected upside down? I'm going to ask it in the opposite order this time. I'm going to ask you this time, what happens when it goes from more dense to less dense? And we could say, we could put in brackets there, it's going to reflect off of something that's not attached. You got a slinky wave, whatever, it's not attached. You're going from more dense to less dense. Is it going to be reflected right side up or is it going to be reflected upside down? Right side up, good, upright in that case. And of course, when you're going from less dense to more dense, and can't spell it, there we go. Less dense to more dense, which is basically the same thing as saying it is attached, then it's going to be reflected upside down, of course, right? So right side up, upside down, keep those straight, please. Now, there's going to be a part that's transmitted as well. Maybe it's a little bit, maybe it's a lot. When it's transmitted, we're looking at this in a slightly different way. Okay, we're not looking about right side up or upside down. It's going to be transmitted right side up, no matter what. All of it is. But something's going to change. Okay, not the orientation of it, whether it's right side up or upside down, but something's going to change. Tell me what's going to change. What's going to change and what's going to stay the same here? What do we know for sure is going to change there, Chantal? The speed. The speed will either increase or decrease. And the speed change, that's the big deal right there, right? That's the most important one. Because the speed changing is what's going to affect the other things that change as well, if they do. What else can change as a result of the speed changing? What else absolutely 100% of the time will change as a result of the speed changing? Yep. No, actually. Okay. The direction will likely change. If it goes in at an angle other than straight on, the direction will change. So 95% of the time, the direction will change as a result of the speed changing. The soldiers are marching in that parking lot, right? And they come in at an angle, the direction of that wavefront is going to change. But if the soldiers go straight onto the boundary between the parking lot and the swamp, then the direction is not going to change. Okay. What's absolutely only going to change every single time? Good. The wavelength will change as a result of the speed. And we're going to say theta is going to change, or the direction is going to change as well. Although in the past we put a little asterisk beside that because it doesn't always change. It depends on the angle we're going in at. What's going to stay the same every single time? Good. Once a wave has been made, the frequency stays the same. So that's what happens when a wave hits a boundary between two materials. What happens when a wave hits another wave? Somebody said it before, I think it was Tyler. What happens when a wave hits another wave? Interference, yeah. We get interference and we have to, if we want to find out exactly what that wave pattern, that resultant wave pattern is going to look like, we have to use something called the superposition principle, which says basically, take the waves you got, add them up. If we take a look at this one, which is one of the examples that we did yesterday, we're gonna just X in these ones right away because there's no overlap of the two waves there. Okay, this one's easy. Now in between, a little bit of overlap. This is 2 above, this is 1 below, so it's going to end up being 1 above. 2 above, 2 below. 2 plus negative 2 is 0. So it's going to be right in here somewhere. 2 above, 2.5. Okay, it's going to be about 1.5. Is that right? Yeah. Sorry, about negative 0.5. 2 above, 3 below is going to give me about negative 1. It's going to look about like this. And the resultant waveform is going to look something like this. What kind of interference is this called? 2 terms, right? One of them is, this is destructive. The other one is constructive. When you're making a smaller wave, it's destructive. When you're making a bigger wave, it's constructive interference. Hey, something we didn't mention the other day when we did this. If these 2 waves are going like this, of course, a tenth of a second later, it's going to look a little bit different, right? What happens after they're not interfering? Do the waves keep going? So wave number 1 just keeps going over here, and wave number 2 keeps going over here? Or does wave number 1 turn around and go back, and wave number 2 turn around and go back? In other words, are they transmitted or are they reflected? If I send a wave pulse down in the slinky, the energy that I transfer will make it down to the person holding the other end of the slinky. It will be transmitted. So when you have 2 waves encountering each other, there's no reflection taking place. Waves will reflect off of a boundary if the medium that it's going to is quite a bit different. But there's no change in medium here. Okay, it's slinky and slinky. The wave just keeps going. So this wave keeps going right through this wave. Once they're past each other, it's as if they never saw each other. They never even turn around and look. Okay, the first wave that we have looks exactly the same as it did before they hit each other. The second wave looks exactly the same as they did before they hit each other. So we know what happens when a wave hits a boundary. We know what happens when a wave hits another wave. We started talking about diffraction yesterday, which is the spreading out of a wave, not the bending of a wave. I think it was you that said refraction, okay, instead of transmission. Refraction is the bending of a wave when you go into a new medium. Diffraction is the spreading out of a wave. Okay, so as it goes through an opening like this, the wave spreads out like this, sometimes more, sometimes less. And there's a few things that affect the amount of diffraction. Sometimes we call it the angle of spread. Okay, this would be about, I don't know, that's almost 90 degrees, almost a 90-degree angle of spread. But sometimes we might get something like this, where you got a whole lot more diffraction. And the angle of spread in that case would be, I don't know, 130 degrees, 140 degrees. When are you going to get that more diffraction? When are you going to get that bigger angle of spread as we did in the second diagram? Is it going to be when you have a bigger opening or when you have a smaller opening? Should I draw it like this, or should I draw it like this with a tiny opening? You guys remember that from yesterday? More diffraction happens when you have a smaller opening. Remember, the analogy that I used was like the rock and the log. Okay, when you throw a rock in the water, it produces like a circular wave. When you throw a log or a brick or a 2x4 into the water, it's not quite so circular. So I'm remembering this by thinking, okay, the little hole is more like the rock, more like throwing a rock. A big opening is more like throwing a 2x4 in there. When you throw the little rock in there, you get close to a circle. So it's going to be closer to a complete circle when you have the little opening right here. More diffraction with a little opening. We're going to say small opening. We're going to say more diffraction, more spreading out, bigger angle of spread. What about frequency? This was the hard one for me to remember, the really hard one for me to remember. And I gave you guys a story yesterday about what happened to me 20 years ago that allows me to remember it. Okay, in the end, you may not remember that story. It may not be helpful to you at all. But in the end, you still have to know how the frequency affects the amount of diffraction taking place. Does anybody remember, either from the story or just because you remember? Some of you are going to be better at remembering it than I am, right? Jordan? Good. So we're going to say low frequency, more diffraction, or we're going to say high frequency, less diffraction. If you remember the story that I told you yesterday, it was when I was listening to AM radio, which is lower frequency radio, I could hear the radio station, right, because it diffracted more. When I was listening to FM radio, which is higher frequency radio, I couldn't hear it because it diffracted less. So when I'm at the bottom of the hill, I need a lot of diffraction. Therefore, I need low frequency waves. What about wavelength? Yep. The lower the wavelength, the more it will diffract? Good. Okay, so the lower the wavelength, the less it will diffract. And we know that because it's exactly the opposite to the frequency, right? If frequency, increasing the frequency causes less diffraction, then increasing the wavelength is going to cause more diffraction, right? Exact opposite effect as it is for frequency. Finally, yesterday, we took a look at the whole combination of diffraction and interference, this idea that we've got two openings. The wave is diffracting through both of them. And then, of course, because you've got two waves, two diffracted waves on the other side, it's producing an interference pattern. Whenever you have a crest meeting a crest or a trough meeting a trough, Megan, it's going to be constructive interference. When you have a crest meeting a trough, it's going to be destructive interference. So yesterday we drew this picture here, gave you a template so that you could draw it yourselves as well. I think we drew a red line wherever we saw a crest and a crest. So bright line and fainter line. Sorry, bright line and bright line, or fainter line and fainter line. Okay, constructive. And so on, right? Same thing happens on the other side. We used a green dot wherever we had destructive interference, where a crest met a trough. Wherever you have the constructive interference, you got big waves, big crests and big troughs. Wherever you have the destructive interference, you don't have anything. They completely cancel out. So you're going to get something looking like this on one side, alternating areas of constructive and destructive interference. And you're going to get the exact same effect on the other side. I just haven't drawn it to you. So you're on an air mattress right here, lying in the water right here. What do you feel? You're bobbing up and down like crazy because the crests are twice as big and the troughs are twice as big as a result of that constructive interference. Okay, what do you feel if you're on the air mattress right here, right beside the other person? Nothing. Calm. It's calm because it's complete destructive interference. Does that make sense? Good?